a fair die is rolled, what is the probability that a 2 is shown? This would be 1/6, since there are 6 possible outcomes, and there is only one 2 on the die. Now, what if we now know that the number shown is a prime number? This extra bit of information changes everything. The question would now be, what is the probability of rolling a 2, given that the number is prime? The sample space, or number of possible outcomes, will no longer be 6. Instead, it would now be 3, since there are now only 3 possible outcomes, which are the prime numbers on the die, 2, 3, and 5. So the probability of rolling a 2, given that the number rolled is a prime number, would be 1/3. The notation would look like this, and would read the probability of the die rolling a 2, given that the number rolled is a prime number. This is what conditional probability is all about. Conditional probability is the probability of one event occurring, knowing that another event has already occurred. The extra piece of information known changes the sample space or denominator entirely. In this example, we could let A be the event that a 2 is rolled, and B the event that the number rolled is a prime number, so set B would have the numbers 2, 3, and 5. A Venn diagram can be used to represent the sets. The probability of A given B would mean the probability of rolling a 2, given that the number rolled is prime. Notice the formula for conditional probability. In this case, the probability of A intersect B would be 1/6, since the number of elements common to both sets is 1 out of 6 possible numbers on the die, while the probability of B is 3/6, since the set B has 3 elements out of a possible 6 on the die. So the probability of A given B is 1/6, divide by 3/6, which is same as 1/6, times 6 over 3. That's 1/3, the same value before we use the formula. The same formula can also be applied to contingency tables. Suppose we want to know the probability that a participant is Republican, given that she is a female. The sample space would not be the grand total of 50. Since we already know that the participant is a female, the sample space would be just females. That's 25. So we put the number of female Republicans over 25 to get our solution. By the way, the same problem could be framed as, what percentage of females in the sample are Republicans? There are 25 females, and 10 of them are Republicans, so 40% of the females are Republicans. Let's look at one final example. Notice we're given the conditional probabilities for A given B, and for B given A. The formula for probability of A given B is the probability of the intersection divided by the probability of B, while the probability of B given A is the probability of the intersection divided by the probability of A. First, we are asked to find the probability of A intersect B. So we use the formula in which we have the most information. That's the one with B given A. We can multiply both sides by denominator, that's the probability of A, and we get an expression for the probability of A intersect B. Replace the probability of A with 1/3, and replace the probability of B given A with 3/5. So our solution for part A is 1/5. To find the probability of B, we'll transpose using the formula with A given B. To do this, we can multiply both sides by the denominator, that's the probability of B, and then divide both sides by the probability of A given B. And now we have an expression for the probability of B. Replace the probability of A intersect B with 1/5, and divide by the probability of A given B, which is 5/7. So the probability of B is 7/25, or 28%. To determine whether A and B are independent, we multiply the probability of A, which is 1/3, times the probability of B, which is a 7/25, to give 7/75, which is not equal to the probability of A intersect B, which we found to be 1/5 in part A. Hence, A and B are not independent. Thanks for watching. Remember to like, share, and subscribe. See you soon.